Let's discuss about excess pressure inside a surface which is having two curvature. When we talk about a surface having two curvature, it will be similar to the situation which I am drawing here. Here you can consider there is a surface which is having one side its radius of curvature r1 and its surface is subtending an angle theta at the center of curvature, and in the right angle dimension or the other side the surface is curved with a radius of curvature r2 with an angle phi subtended at the center of curvature. And in this situation, say one side there is liquid and other side there is gaseous media or air. We can say as the bulge is in upward direction inside, if we consider a point A and outside we consider a point B, we can say that pressure at point A will be more than pressure at point B. And if we find out the net outward force acting on this liquid surface, so we can simply write net outward force on liquid surface is this F out can be written as the excess pressure inside will be PA minus PB multiplied by the surface area if we consider theta and phi to be small. If these are small angles, we can take up this dimension as r1 theta and this dimension as r2 phi. So this can be written as r1 r2 theta phi. This is the net outward force acting on it. And due to surface tension on this surface, we can say this is the side where surface tension force will act, and on this side tangentially in this dimension surface tension force will act. And if we draw it independently, we can say for the side of theta the situation is this. If we just draw the sectional view of this side where the surface is subtending an angle theta, this radius is r1, so the force of surface tension on this can be written as T multiplied by, if we talk just about its angle, if this angle is theta and the radius is r1, or we can simply state on this the stretching force will be equals to T into the length of the other side, which is r2 phi, and this is also T into r2 phi, the net force acting on it, and the horizontal components will balance out. Net force in inward direction will be the vertical component of this T r2 phi. If this angle is theta, we can say this angle will be theta by 2, and here this is also theta by 2. So net inward force can be written as net inward force on liquid surface due to surface tension is this net inward force on one side we can write as T into r2 phi multiplied by, we talk about its vertical component is sine of theta by 2, and on both the surfaces it is acting, so it must be multiplied by 2, plus similar force we must use for the other side where this r2 radius and phi angle is subtended by the surface. So in that case we can write as T into r1 theta multiplied by sine of phi by 2 multiplied by 2. So in this situation we can see the result we are having is, as this theta and phi are small angles, the sine can be omitted for small angles, and we can write T into r2 phi multiplied by sine theta by 2 can be written as theta by 2 gets cancelled out, so it will be theta plus T r1 theta multiplied by, here it will be phi, so the result will be T phi theta multiplied by r1 plus r2. This is the net inward force which is acting on the surface due to surface tension. And here we can state for equilibrium of the liquid surface, the two forces must be balanced. Let's continue on the next slide. So in this situation, we can write for equilibrium of liquid surface, we must use F outside is equals to F inside. So in this situation, as we have calculated, F outside is PA minus PB multiplied by R1 R2 theta phi, which should be equals to the inside force, which is due to surface tension. We have calculated as T theta phi R1 plus R2. In this situation, this theta and phi gets cancelled out, and this PA minus PB, we can write the axis pressure inside, which can be written as T. R1 R2 can be taken on the other side of equality. It will be 1 by R1 plus 1 by R2. This is the expression we use for axis pressure inside a surface which is having two curvatures, and if rather than one side liquid, if it is a film, we can write if this surface is a film, then we can use this axis pressure as twice of T, 1 by R1 plus 1 by R2, as it will be twice of this value, because in case of a film there are two surfaces. A very basic application of this result we can use, that is axis pressure inside a cylindrical surface of liquid. Say if we are having a cylindrical liquid surface, there is a liquid which is in the shape of a cylinder, where the radius of curvature of lateral part of cylinder is R. Then in this situation we can say one curvature is R and other surface is flat, or other curvature is infinite. So in this situation we can take its R1 is equals to R and R2 is equals to infinity, because the surface is flat. So axis pressure can be given as T into 1 by R plus 1 by infinity. So this will be T by R. So if inside there is a point A, outside there is a point B, we can write PA minus PB, the axis pressure inside a liquid body having cylindrical shape. Then axis pressure inside the surface can be written as T by R. And for a cylindrical film, if we talk, then we can directly write axis pressure will be 2T by R, because in case of a cylindrical film, there will be two surfaces, one is outer and other is inner, so axis pressure will get doubled.